we'll see. Right. So I think all of you can see the screen. All of you are able to see the screen, right? So yesterday, right, I posted a video that is numerical problems, which is solved by Prasad sir. That's what I have posted, right? In fact, I was supposed to post 2 other videos, right? I had some issue while compiling that video. The audio was not right audible, but even then, some of you have watched it, and some even have liked. I don't know how they could do that, right? Anyhow, thank you so much for right that. Okay, fine. So now we were discussing about a direct method of FM demodulation. So in direct method of FM demodulation, what happens is, right, the frequency variation, right, the instantaneous frequency variation, it is actually what it should be converted into, right, amplitude variation. That is what we have to do. In frequency modulation, what we are doing is amplitude variation is captured as frequency variation. In demodulation, we should do the reverse. So for that, we'll be using a frequency discriminator circuit, right? A frequency discriminator essentially consists of a slope circuit, right, and a envelope detector. And we have seen what are the right about how or what should be the transfer function of an ideal slope circuit, right? And we have considered the transfer function of ideal slope circuit as h1 of f, right? And if we are giving s of t as input to this ideal slope circuit, our s of t is nothing but what our FM signal, right? Then the output is s1 of t. So we wanted to try and find out what is as s1 of t. If you know the s1 of t, then if we can identify what is the envelope of s1 of t, then we can easily come to a conclusion how a frequency discriminator works. The difficult part is analyzing this. You are giving s of t to a slope circuit and giving s1 of t. What is that s1 of t? That we have to find out, right? So for that, we told we have an issue. This s of t is a band pass signal, right? And of course, h1 of f also is a band pass frequency response, right? So in order to tackle that, we have some AC method, that is wherever we have signals and systems in band pass, we can, for convenient, represent it as its equivalent low pass counterpart, right? So 1 second, people are trying to join. I have to just admit them, otherwise they won't. Yeah, okay. Fine. Yeah, so let them join. Right. So equivalent low pass counterpart. So for that, what we did is I told how we can find out the low pass equivalent of a band pass signal. So if s of t, okay, maybe I'll just accept whoever is trying to join in. Yeah. Okay. So of t is the band pass signal. S tilde of t will, right, notate the equivalent low pass signal. This, and if you take Fourier transform of that S tilde of t, you will get S tilde of f, right? And so then what we have is, so this system S1 of t given to H1 of t and giving S1 of t as S of t given to H1 of t and giving S1 of t as output, we can write in low pass equivalent, that too in frequency domain, as you are giving a signal with low pass signal with spectrum S tilde of f to a low pass equivalent circuit of the slope, low pass equivalent of the slope circuit with transfer function h tilde of f, and we are getting an output s1 tilde of f. So this is the low pass equivalent of the band pass signals and system. So in this case, we can write, right, so this one, right, s1 tilde of f, low pass equivalent of s1 of t, will be equal to half times h1 tilde of f times s tilde of f, right? So this, I request you to what, accept it as such. Why? Because this details, right, that will be your first module in your digital communication, right? So just remember, right, s1 tilde of f is half h1 of f times s tilde of f. So if I'm going to explain this, it will again take 1.5 hours, right? So I'm not doing that now, but you can just relate it. How you can relate it is, normally if you give right, if you consider an LTI system with impulse response h1 of t and input s of t, the output will be S of t convolved with h1 of t, if this is the band pass case. And in frequency domain, what will happen is it will become S of f into h1 of f, right? It will become S of f into, it will become S of f into h1 of f. But when you are using the low pass equivalent, there is an additional half, right? There is an additional half. Just keep that in mind. I'm not going into details of that, right? But this result is what we are using, right? Then, so once we have this S1 tilde of f, then what we can do is we can take inverse Fourier transform of this S1 tilde of f. We'll get S1 tilde of t. So this is our, right, low pass equivalent of S1 of t. This S1 of t, as I've told, it is supposed to be a hybrid signal. Hybrid signal in the sense the slope detector output is a hybrid signal. When I say hybrid signal, it actually what has AM plus FM. AM, when I say, normally S of t has constant envelope, its amplitude is a constant, but when it is passed through a slope circuit, what happens is, according to the frequency variation of S of t, there will be amplitude variation in S1 of t. This S1 of t will have a varying amplitude as well as varying frequency, right? So this varying amplitude part is what we are interested in, right? Why? Because if we have an envelope, right, which is varying with respect to the message, we can use an envelope detector to obtain the message back. So what we did is, FM signal with constant envelope is transformed into signal with time varying envelope, so that we can detect the envelope. That envelope will give us information about message signal, right? So for that, we obtain the low pass equivalent of S1 of t, that is S1 tilde of t. Then from low pass equivalent, we are getting back actually what the S1 of t, the band pass signal as such, and then we can write it in standard form, right? And identify what is its envelope, right? So that's our idea. That's what we have discussed in last class, right? So then I request all of you to continue taking down notes along with me itself. So, but these things you might have already written. So our S of t, its standard form is AC cos 2 pi fct plus 2 pi kf integral 0 to m of tau d tau, right? That is S of t. And the Fourier transform of S of t, I'll represent as S of f in further discussions. And the low pass equivalent of S of t will be represented as S tilde of t. And we found out in last class, we have seen how to obtain the low pass equivalent of this, right? So we have written it as AC times real part of e power j something. Then we suppress the real part and e power j 2 pi fct, and remaining what we were getting, that is the low pass equivalent, right? Then so this result is there, so we need to use it later, right? And if you take Fourier transform of this, whatever we are getting, we can represent it as S tilde of f. So we don't want to find out the Fourier transform of this. There is a reason, right? So what we need is, we need this S tilde of t, right? And just keep in mind, S tilde of f will be Fourier transform of S tilde of t, right? So now we will come back to the transfer function of slope circuit, right? So we have seen transfer function of slope circuit. It is purely imaginary. Because of that, we have actually what, j times whatever be the magnitude, right? J times whatever be the magnitude, and it is defined over a prescribed interval. So our prescribed interval is centered around plus fc and minus fc, right? A frequency range of bt hertz around plus fc, and a frequency range of bt hertz around minus fc. So that is fc minus bt by 2 to fc plus bt by 2. That is in the positive side, and fc minus bt minus fc minus bt by 2 to minus fc plus bt by 2. That is in the negative side, and it should be 0 elsewhere. So we have even plotted it. The plot, right, of h1 of f by j, it was like this. You can see this can act as a frequency discriminator. If you see over this range of frequency, for individual frequency component, right, the gain of the spectrum, gain provided by the spectrum is different, right? So it will treat different frequencies differently. So we can discriminate among frequencies. That is actually what a slope circuit or frequency discriminator, right? So what we need here is, right, as per our requirement, we need to find h1 tilde of f. We need to find h1 tilde of f. So for that, right? How to find h1 tilde of f is the next question. So to find h1 tilde of f is also, right, it's a lengthy process, right? For that, right, we can take h1 tilde of f, h1 tilde of t in time domain. H1 tilde of t will be actually what? H1 of t plus j times h1 cap of t. This h1 cap of t is nothing but what? Hilbert transform of this h1 of t. H1 tilde of t, h1 cap of t is nothing but Hilbert transform of h1 of t, that multiplied with e power minus j 2 pi fct. This is actually what in time domain h1 tilde of t. So this thing I have discussed in detail when I discussed the topic Hilbert transform and pre-envelope and complex envelope, right? So please do refer back to that video, right? But even though it's not required actually, right? This part, whichever I have written in this red, it's not exactly required for you, but right, some of you may be thinking how this came, but at least some of you may be okay, you will be able to what settle down with whatever I say, but at least some of you may be thinking. For them, I'm telling, right, this is the time. This is how you can obtain the low pass equivalent of the band pass impulse response h1 of t, right? H1. So now, if you take Fourier transform of this Fourier transform of this entire expression, right? Fourier transform of h1 tilde of t is h1 tilde of f, capital H1 tilde of f. Then if you take Fourier transform of h1 of t, that will be h1 of f. Then j will be j as such. Then this h1 cap of f is nothing but what? Hilbert transform of h1 of t, right? And I've discussed Hilbert transform. What it does is it converts the phase of all positive frequency content in a given signal by an amount minus pi by 2, right? So minus pi by 2. So this the frequency domain representation of h1 tilde of t, that is h1 tilde of f, will be nothing but what? Minus j signum of f times h1 of f, right? Minus j signum of f times h1 of f, right? So this is the this is the Fourier transform of h1 tilde of t. So what I've done is I've written the time domain expression, I've obtained the Fourier transform. Then there is a multiplication factor e power minus j 2 pi fct. There is a multiplication with e power minus j 2 pi fct. So this multiplication with e power minus j 2 pi fct in time domain, right? It will become actually what? Frequency shifting in frequency domain, right? So if you are multiplying with e power minus j 2 pi fct, it is equivalent to what? Shifting the frequency by an amount minus fc, or shifting left by an amount fc, right? So I think someone is trying to join in. Okay, someone tried to join. Okay, fine. Yeah. So this multiplication with e power minus j 2 pi fct will become actually what? Shifting by an amount minus ft, so minus fc. So it will be shifted back to origin. So that's what I have written here, right? So what happens then is this h1 of f plus this j into j will become minus 1. Minus of minus 1 will be actually what? Minus of minus 1 will be plus 1. So that becomes plus this minus j into j will become plus 1. Then signum of f into h of f. So what actually is signum of f? Signum of f is this, right? It is 1 for positive frequencies and minus 1 for negative frequencies. So if you're multiplying h1 of f with signum of f, what happens? The part of h1 of f which is towards the right of 0, or positive part of h1 of f, will remain as such, and negative part of h1 of f will become actually what? Minus h1 of f, right? Positive part will become remain as such, and negative part will become actually what? Minus h1 of f. So we are adding h1 of f with signum of f into h1 of f. So what will happen? For negative side, it will be h1 of f minus h1 of f. So it will get cancelled. Negative side, it will get cancelled. And for positive side, it will be h1 of f plus h1 of f. So that will be 2 times h1 of f. That's what I have written here, right? 2 times h1 of f. So please do take down, right? So if you need more time to take down, right, I'll give you time. Why? Because you can't find this in textbook or anywhere, right? Or else you will have to refer your higher semester textbook, right? But if you know this, the things becomes easy. You don't have to by heart anything, right? So please note down, right? and later on if you have any doubt you can ask, right? So I'm giving you ample time to what note down, right? So please do note down. So so this low pass equivalent of this band pass spectrum becomes actually what, 2 times h1 of f. But what happens is the negative frequency part, it gets cancelled. Negative frequency part, whatever is there, it gets cancelled, and positive frequency part, whatever is there, it gets doubled, right? So if you remember what was h1 of f, I'll draw the h1 of f again here, right? h1 of f was like this, right? So negative frequency part, whatever was there, it got cancelled, it is not there. And in positive part, what is there, it became actually what, double, right? It became double. So that, then what we should do, because of this e power presence of e power minus j 2 pi fct, we have to shift this left by an amount fc, right? We have to shift this left by an amount fc. So this is actually what, fc, and this is fc plus bt by 2, and this is fc minus bt by 2, right? So if you shift it by an amount fc, what is that you will get? You will get something like this, right? You will get something like this. It will have amplitude which is equal to what, twice that of h1 of f for positive side, and it will be centered at origin. It will span from minus bt by 2 to plus bt by 2, right? Where bt was nothing but the bandwidth of the fm signal, which we assume, right? So this is the low pass equivalent. So this is how we'll get. So this thing, whatever I have told in sentence, right? It says actually what, h1 of f minus fc is equal to twice h1 of f for f greater than 0. What does that mean? This h1 of f, if you shift right by an amount fc, this h1 of f, if you shift right by an amount fc, you will get twice h1 of f, right? This h1 tilde of f, right? The meaning is, right? So even though I have written it mathematically, right? The meaning is this h1 tilde of f minus fc means actually what, it is shifting, right, along the independent variable. So h1 of f minus fc is h1 tilde of f shifted right by an amount fc will give you twice h1 of f. So that's what I have written here. Only this, right, only this statement they have mentioned in your textbook. These things are missing. So those who want to know how it came, right, can note down, right? I don't expect what you will be able to appreciate it at the first time itself, right? Why? Because it's a completely new concept, right? I at the same time I can't spend more time on this because it's, right, not directly a part of your syllabus. It's a prerequisite which appears in actually what, your higher semesters, right? So maybe, but that is required. We don't have any other go, right? So this result they have mentioned. So meaning of the result, if you have to interpret, you should know these things, right? So I request you to note it down, right? Take some time and try to analyze. And if you're getting some doubt, you can actually what, ask questions, right? I'll help you to what, maybe if you are asking me doubt in person, I'll be able to what, spend more time. So now in regular class, right, we'll do only this much, right? I'm giving you an option again and again. I'm stressing, please ask doubt if you have, right? Please don't feel reluctant, right? So okay, now with this, what we got now, this low pass equivalent is twice h1 of f for f greater than 0. So twice h1 of f. So for f greater than 0, h1 of f was actually what, j 2 pi a f minus fc plus bt by 2, right? This was h1 of f. So twice h1 of f will be what, j 4 pi a f minus fc plus bt by 2, right? Then what we have to do, we have to shift it left. So this thing is centered at fc. If I am shifting it left by an amount fc, it will be centered at origin. So what will happen is this fc will disappear, right? Shifting right by an amount, shifting left by an amount fc is actually what, adding fc, right? So I'll again x of f, right? X of f plus fc means, x of f plus fc means whatever x of f was there, that will be shifted left by an amount fc, right? Similarly, x of f minus fc means that will be shifted right by an amount fc, right? So that's why this fc is not there. So h1 tilde of f is j 4 pi a f plus bt by 2, that is from minus bt by 2 to plus bt by 2, and it is 0 elsewhere, right? So this is how you can plot this, right? So this is h1 tilde of f by j. Its slope is actually what it is, right? 4 pi for the slope of h1 of f was 2 pi a. Right now the slope is 4 pi a, which means the slope has actually what doubled. Right, the slope has doubled, and maybe because of this, there is a factor of half. Right, there is a factor of half in the frequency response of S1 tilde of F. Right, so I'm not confusing you people. I at least, right, I request everyone to take this down, try to analyze, take some time. Right, you can watch this video maybe again and try to analyze. And even then, if you're getting doubt, please feel free to ask. Right, otherwise, if you're okay with right these results and you're ready to accept it as such, you are able to appreciate it, right? Okay, fine, no problem. And so we have this h1 tilde of f. So now what we have is, right, so we can write s1 tilde of f is equal to half times h1 tilde of f into s tilde of f. So we didn't find out this s tilde of f. That is not required. Why? Because we'll write this expression, then we straight away we'll take inverse Fourier transform, right? So now s1 tilde of f is s1 tilde of f is equal to, right, say maybe this h1 tilde of f has two cases, right? h1 tilde of f, as you see, right, one is between minus bt by 2 and plus bt by 2, and the other case is elsewhere, right? So it is half times, right, j 4 pi a times f plus bt by 2, right? F plus bt by 2 times s tilde of f, right, 4 minus bt by 2 less than or equal to f less than or equal to plus bt by 2, right? And it is 0 elsewhere. If you're multiplying, right, 0 elsewhere. So this is what s1 tilde of f, right? So it's defined, it's non-zero only during this interval. So maybe we'll consider that. So it's half and this 4, right? So maybe we can write s1 tilde of f, right? It is equal to j 2 pi a. Maybe I'll expand it now. J 2 pi a f times s tilde of f plus j 2 pi a, and this there is a bt by 2, right? So bt by 2 and that 2 will, this 2 will get cancelled, right? Maybe I'll write that bt by 2. So this 2 and 2 will get cancelled times s tilde of f. So this is what we have, right? This is what we have, right? So again, I request all of you to what take it down along with me. So this s tilde of f is j 2 pi a f s tilde of f plus j pi a bt s tilde of f, right? So now what we can do is we can take inverse Fourier transform of this entire thing. Inverse Fourier transform of this entire thing, right? So inverse Fourier transform of s1 tilde of f will be what? S1 tilde of t, right? We are going to take inverse Fourier transform. So S1 tilde of f, its inverse Fourier transform is S1 tilde of t, right? Then what we have is j 2 pi f into s tilde of f, right? So we have a property of Fourier transform, right? We have a property of Fourier transform. If Fourier transform of x of t is x of f, right, then Fourier transform of d by dt of x of t, it is j 2 pi f times x of f, right? So there is a property, you might have studied it in signals and systems, not might have, you have studied it in signals and systems. So that property is what we are using now, right? So Fourier transform of derivative, right? So if x of f is Fourier transform of x of t, then Fourier transform of derivative of x of t, it is actually what? J 2 pi f. Fourier transform of derivative of x of t is j 2 pi f, right? So a straightforward evidence of this property is, right? So wherever you are dealing with, say, RLC circuits and all, right? So you have actually what, when you are writing phasors, right? You are writing j omega l, right? 1 by c omega, all those things. That is actually what, uh, because of this factor, right? So whether it is actually what a phasor or uh, say Fourier any transformation, right? So because of this derivative property, that multiplicative factors are coming. I'm just leaving it to you, like to think through, right? So d by dt of x of t, it will be, its Fourier transform will be j 2 pi f into x of f. So here we have j 2 pi f into s tilde of f. This a is a constant. So what will be the inverse Fourier transform of that? It will be nothing but what, a times, right, d by dt of s tilde of t, right? So j 2 pi s f into s tilde of f, its inverse Fourier transform will be d by dt of s tilde of t, right? Then plus what we have is j 2 pi a bt, that is a, those are j the pi a bt, everything are constants, right? So then we can write j pi a bt times s tilde of t. So this is what is s1, right? So this is s1 tilde of t. So this is what, this is how we found out, right? So initially, right, what we had is h1 of f and s of t, right? So from that we found out actually what, s1 tilde of t, it is low pass equivalent of our band pass signal, right? So now we know what is s tilde of t, right? We know what is s tilde of t. We know s tilde of t, it is equal to ac e power j 2 pi kf times integral 0 to t m of tau d tau, right? So this is s of t. Now what we can do is we can substitute it here, right? We can substitute it here. So we'll substitute it here in the expression of s1 tilde of t, right? So s1 tilde of t becomes a times d by dt of s tilde of t is ac times e power j 2 pi kf integral 0 to t m of tau d tau, right, plus j pi a bt again ac e power j 2 pi kf integral 0 to t m of tau d tau, right? So this is what we have, right? So now what is d by dt of this d, so ac is a constant, so we can take it out actually, a times ac, then d by dt of e power j 2 pi kf integral 0 to tau m of tau d tau, it will be, right, or d by dt of e power something, e power j times, say, f of t will be e power j times f of t into f dash of t, right? So this will be e power j times f of t into f dash of t, right? So this is what we have to do. So it is e power j 2 pi kf into 0 to t m of tau d tau, right? So maybe I'll write it in bracket into d by dt of e power j 2 pi kf integral 0 to t m of tau d tau, right? Then plus the second term j pi a bt. I know the expression is becoming too complicated, but nothing is there, right? You have to just take your pen and paper and write. That's it, right? J pi a bt ac e power j 2 pi kf integral 0 to t m of tau d tau, right? So this is what we have now. So you can see in both these a ac e power j 2 pi kf, right? Those are common, so we can take them common, right? So it is a ac times e power j 2 pi kf integral 0 to t m of tau d tau. It's common, right? So then in the first term, what is remaining? D by dt of e power j 2 pi kf 0 tau m. So what will be that? No, not this e power j. It is integral of sorry, derivative of, right? So it is derivative of only what is the argument of that e power j, right? So this I by mistake I wrote e power. That e power is not there. So just refer back to the property I told. Derivative of e power j of f of t. It will be e power j f of t times derivative of f of t. That is f dash of t, right? So yeah. So it will be, what is d by dt of j 2 pi kf integral 0, right? So this j 2 pi kf, everything is constant. D by dt of integral 0 to t m of tau d tau. What is that? Can anyone tell me? J2, so it is j 2 pi kf 2 pi kf into what is d by dt of integral 0 to t m of tau d tau, right? Now I want all of you to type what is the result in chat window. We have used it even before, right? Maybe while we are deriving the spectrum of, sorry, yeah, obtaining the time domain expression of wideband FM also we did that. So my question is, what is d by dt of, yeah, so Shreyas has typed it is m of t, right? It's correct. We have discussed it many times before. And thank you, Shreyas, for giving answer. Right, so j 2 pi kf into m of t, right? Plus then what is left out here in this one, sorry, pi bt is there, right? On pi bt is there, right? Pi, only pi bt, or yeah, j pi bt is there, right? What is left out then? It's pi j pi bt, I think. Right, so it is j pi bt, j pi bt, right? So that is what is left out now, right? So this is s1 tilde of t, this is s1 tilde of t, right? So if I'm further simplifying it, or rearranging it, right, I will get s1 tilde of t. Again, we have actually what, some common terms, pi, j pi, all those things are common, right? And even if you take now j pi bt, right, as common from this outside, right, let's see what happens, right? So if you take j pi bt as common from this outside, so it will become something into 1 plus, right, something. So after rearranging, right, after rearranging that, what I'm doing is I'm taking actually what, or I'm dividing both the right terms, right, with j pi bt, dividing and multiplying both the terms with actually what, j pi bt, whatever, right? So what I'm getting is s1 tilde of t, it is equal to, right, j pi bt a ac times, so this j pi bt will become 1 plus So if you right take j pi bt, pi is already there, right? Pi is already there, right? Then it will become j to kf by bt, right? So j is also taken out, so it will become 2 kf by bt, 2 kf by bt into m of t, 2 kf by bt into m of t, right? This is what is s1 tilde of t, right? This is what is s1 tilde of t, right? So now if you have to get right s1 of t from s1 tilde of t, right? If you have to get s1 of t from s1 tilde of t, what you should do is, right? So from this, it is actually what exactly the reverse of how we got s1 s tilde of t from s of t, right? So I'll just write here s1 of t will be, what you should do is, if you remember, we have omitted a real part, so we should bring in the real part here, right? Then we also omitted an e power j 2 pi fct. If you remember, we also omitted an e power j 2 pi fct. So real part of it will be real part of s1 tilde of t, right? So we also omitted an e power j 2 pi fct. So I should introduce that e power j 2 pi fct here, right? For j 2 pi fct here. So to get s1 tilde of t from s1 of t, right? What I have done is I have written s1 of t as real part of something. Then from that I have omitted real part and e power j 2 pi fct, those things, right? So in order to get back, I should do exactly the reverse, right? So it's actually what converting a sinusoid into phasor and how to convert it back, right? It's the same process, right? So if you can extend, so if it is a single tone signal or a single frequency signal, how you are converting a single tone signal into a phasor and converting it back into what real instantaneous form. Similarly, if you can extend that concept to a band pass signal will have a range of frequencies. It's not a single frequency. Similarly, if you can extend that concept to a band pass signal, right? What we'll get is we'll get this analytic signal or low pass equivalent, right? So that's what you have to keep in mind. So S1 of t is real part of S1 tilde of t in d power j 2 pi fct. So it is equal to real part of, what is S1 tilde of t now? It is j pi bt ac, right? S1 tilde of t is nothing but what? J pi bt ac into 1 plus 2 pi kf into m of t, right? So it is real part of j pi bt a AC into 1 plus, say I'll keep it as a double bracket, 2 kf by bt into m of t, right? This into e power j 2 pi fct, right? So this is what, so but e power j 2 pi fct is actually what? Cos 2 pi fct plus j sine 2 pi fct. Now what you can do, next step what you can do is, I won't do that step, right? By Euler's relation, e power j 2 pi fct is nothing but what? Cos 2 pi fct plus j sine 2 pi fct, right? So already we have a j here, right? So you'll get, right, if you solve this, you will get something like this, a plus jb, right? You will get like this, a plus jb. So real part of a plus jb will be actually what? A. That is what you're doing, right? And also one thing, multiplication with j, it is equivalent to what? A phase shift of one angle 90 degree, or it is equivalent to a phase shift of e power j pi by 2, right? So multiplication of j, you can replace it with actually what? E power j pi by 2. It's equivalent to what? A phase shift of pi by 2, right? So with these two ideas, right, what we can do is we can get back s1 of t. We can get back s1 of t is equal to, right, s1 of t is equal to, I'll write it here, pi bt a ac, right? Then 1 plus 2 kf by bt times m of t times cos 2 pi fct, cos 2 pi fct plus 2 pi kf into integral 0 to t m of tau d tau, right? Then there is a plus pi by 2, right? There is a plus pi by 2. That pi by 2 is from this actually what? Multiplication with j, right? Multiplication with j you can write as actually what? Into e power j pi by 2. So e power j 2 pi fct into e power j pi by 2 will become actually what? E power j 2 pi fct plus pi by 2, right? So these two when multiplied will become e power j 2 pi fct plus pi by 2, right? That if you expand using Euler's formula, so right, you can try it out. You can try it out as a homework. So for sure, it's even though the expressions are a bit lengthy and looks complicated, right? If you try it out step by step, for sure you will get these results. You don't have to actually what simply mug up or by heart anything, right? So these are we are trying to what apply whatever we are supposed to know here, right? That's it. Yeah. So this is the expression for S1 of t. So this S1 of t, you can see now, right? You can compare it with our standard AM signal, right? As in standard AM, SAM, right? SAM of t, it is equal to what? AC into 1 plus KA M of t cos 2 pi FCT, right? If you compare it with this, the carrier amplitude is equivalent to what? This thing, right? Pi BT A times AC. Then 1 plus K M of T. This is actually what M of T is our message. K was amplitude sensitivity. So here amplitude sensitivity part is 2 KF by BT, and M of T is our message. Right, one is there as such, and cos of something is there. Of course, right here, this is again a sort of actually what signal with instantaneous frequency as a function of time, right? But we are not bothered about this. Whatever it is, right? It's a cosinusoid, right? Even if its frequency changes or not, what happens when you pass it through a diode, right? It will clip off the negative part, right? An envelope detector, it's nothing but what? It has a diode followed by a low pass filter, right? So whenever you pass this any cosinusoid of whatever be its frequency, right? What happens is it will clip off the negative part, and we are interested in the envelope, right? We are interested in the variation of the peak values of each half cycle, right? So that's what we are interested. So the variation of peak values of each half cycle will be determined by this particular term, right? So now if you remember, if you relate it with actually what the first type of demodulator which we have learned, differentiator followed by envelope detector, right? The slope detector also does almost the same thing. It actually what differentiates, right? And followed by it is fed to an envelope detector. So this S1 of t is what is given to an envelope detector. So the envelope of this S1 of t is this much, right? Envelope of this S1 of t is this entire thing. And we know there is a constraint for envelope detector to work satisfactorily. There should not be any what phase reversal, right? For no phase reversal, we know the condition, right? 1 plus K into M of T, right? That should be always greater than 0. So that condition again, I am not discussing, right? Same thing I've discussed in not the previous video, the video before that when we discussed about a general FM demodulator, right? So, and please don't think I'm right in between. I'm skipping some steps. Why? Because it's video that those videos are already available online, right? So you can anytime you can refer it back. So I need not spend much time on repeating things. But maybe that is why I'm not actually what some aspects which are already discussed. I may not discuss again, right? Right. Okay. Fine. Yeah. So this SAM. So this is the envelope. So now we'll. This signal can be detected satisfactorily if it satisfies this condition, that is 2 kf by bt times m of t, or 2 kf by bt times mod of m of t should be always less than 1. So this is actually what condition for a envelope detector to work satisfactorily. So this it comes from this, right? So 2 kf by bt times m of t should be less than 1. So we have seen one case actually. In the previous we have seen a case of FM modulator with frequency, carrier frequency 100 megahertz, right? And FM is equal to say 15 kilohertz, right? So we have seen to satisfy this condition, it is not that difficult. It is quite straightforward, right? So um, the envelope is, so maybe I can write the envelope as actually what, pi bt, yeah. So the envelope is this much, pi bt ac times 1 plus 2 pi kf into m of t, right? So that is the envelope. So I'll write the envelope is pi bt ac times a into 1 plus 2 kf by bt times m of t. This is the envelope, right? So now m of t, this is our actually what message signal, right? So but it's actually what I told in last class itself. If I have to get the original message signal m of t back, I should do some signal conditioning, right? I should do some signal conditioning, right? We have actually what it's, if you expand this, it's equal to what, pi bt a ac plus this bt and bt will get cancelled, right? So it will become 2 pi kf a 2 pi kf a ac times m of t, right? So you can see there is a, there is some gain factor, there is some actually what scaling factor. At the same time there is actually what, a dc shift, right? This is actually what a dc shift, or maybe we can also call it as actually what, bias term. There is a dc shift or a bias term, and there is also actually what, some gain or weighing factor, right? So how to eliminate this, how to eliminate this part, right? To eliminate this part we have a we have a technique, right? To eliminate that part we have a technique. That's where actually what the concept of a balanced frequency discriminator comes, right? So for that what we should do is, right, uh, a balanced frequency discriminator is nothing but what, to eliminate this bias term, what we can do is, right, we can have a scheme like this. So we have a, a slope circuit with frequency response h1 of f, right? And we'll use another one more slope circuit with frequency response, say h2 of f. Then we'll have an envelope detector on the upper branch. We'll also have an envelope detector on the lower branch. Then what we can do is we can simply, right, use a summer, right, sorry, use a summer, right? So and we should subtract the lower branch result from the upper branch result. Then we will get the baseband signal, baseband message signal, m of t we will get back, right? So here we are giving fm wave, right here. So this is actually what the circuit of a balanced frequency, block diagram of a balanced frequency discriminator, right? So why there is a additional parallel path here? Why? Because there is a DC shift or a bias term, right? If you have to eliminate that, what we can do is, and we can have one more slope circuit with this frequency response h2 of f. So what is that h2 of f? That is the question now, right? If you remember, h1 of f was like this. H1 of f was like this, right? So now h2 of, this is h1 of f. This is h1 of f, and h2 of f, right? It is um, or h1 tilde of f we can, right, right. So maybe, right, I should not. So this H2, right, this H1 of f and H2 of f are related as H2 tilde of f should be equal to H1 tilde of minus f, which means, so H1 tilde of f is this, H1 tilde of f is this, H1 tilde of minus f will be actually its say mirror image, right? H1 tilde of f minus f will be its mirror image, a filter like this. So this will be H2 tilde of f. So in order to get H2 of f, what you should do, you should shift it right by an amount Fc, right? You please think of it, right? So this is the condition which should be met by the frequency responses H2 tilde of f and H1 tilde of f, so that this DC bias or the DC bias part will be removed. A DC bias is nothing but if you have a sinusoid, right? If this is sine 2 pi fct, what does mean by 1 plus sine 2 pi fct? 1 plus sine theta. What will happen? This entire thing will be clamped up, right? This entire thing will be clamped up, right? That is actually what bias or DC shift, right? So same thing here as well, right? This m of t, whatever be the waveform, if you add a constant to it, if you add a DC shift to it, or if you add a bias to it, it will be clamped up. You should clamp it down. So in order to clamp it down or eliminate that DC term or bias term, right, we should have a balanced frequency discriminator. That balancing can be accomplished by what? Adding a slope circuit, an additional slope circuit in parallel to what the given slope circuit, and subtract the resultants. Then this part will be removed. So maybe you can just try it out. So in that case, here, if this is actually what S1 tilde of t, and this is S2 tilde of t, right? So this S2 tilde of t will be, right, or mod of S2 tilde of t, it will be equal to, you can, right, by following same method, you can find out pi Vt AAC times 1 minus 2 kf by Bt times m of t. So what happens if you are subtracting? The other one was 1 plus, the other one was 1 plus, and here it is 1 minus. So when you are subtracting this one from the first one, what happens? The first term will be cancelled, the second term will become actually what? Double, right? So we can write, if S0 of t, right, if S0 of t is our say balanced frequency discriminator output, we can write S0 of t is equal to, we can write mod of S1 tilde of t, right? Mod of S1 tilde of t is same as that of the envelope, okay? It is same as that of envelope, mod of S1 tilde of t minus mod of S2 tilde of t, and that will be equal to, you can find out, 4 pi AF A AC times m of t. That will be equal to 4 pi kf A AC times m of t, right? So this will be envelope detector. So there will of course be some scaling factor, but right, the information can easily be even if a signal is it's equivalent to what? Amplifying or attenuating a signal. Even if a signal is amplified or attenuated, right, the information lies in amplitude variation, right, or information lies in the slope, right? So that of course actually what that information we can get back easily, right? So that's not a problem. So this is the frequency discriminator output, right? I can't, right, it was never asked in exam before, but there is a very good chance that, right, they can ask this time, right? So okay, fine. So this is we have seen the block diagram now, right? So we have a a practical method of realizing this balanced frequency discriminator. So here we'll give S of t, that is FM wave. We can give here to input of a say a transformer, right? A center tap transformer, right? Then we should have it's a center tap. It should be a center tap transformer. We should have, right, a primary part, right, and two parts, upper part of primary and lower part of primary, right? So then here we should have a filter, right, then followed by, right, envelope detector, right. So envelope detector is a diode, right? So diode. So this is right, a slope circuit. This is slope circuit. This is again actually what, a slope circuit, right? This part, this LC part becomes a slope circuit. What it can do is it can uh, transform the instantaneous frequency variation into amplitude variation, right? Of course it's possible, right? So with respect to, with the what the gain of an LC circuit, it of course changes with respect to what frequency. It's a function of frequency, right? So this first part, this LC tank part, act as actually what, slope circuit. Then we have this envelope detector. Envelope detector is nothing but what, a diode followed by a low pass filter, a diode followed by a low pass filter, right? Right. So this is how we can practically implement a balanced discriminator. So you might have noticed wherever we are using a balanced thing, so there is actually what, a balanced center tap transformer, right? So this part, right? So it's actually what, equivalent to the block diagram. So this is the block diagram, and this is the circuit, right? The actual circuit. So about the explanation of the circuit, I'll be posting a video now. It's almost 3 o'clock, right? Maybe we'll just try and wind up the session, right? So I can understand, right, whatever we have done. It's a slightly complicated derivation. It involves actually what, some say complicated like mathematical prerequisites, right? But even then, if you have taken it down, right, you'll be able to what, slowly you can study this. So maybe this is one of the what, maybe in critical concepts in second module, right? So what we'll do is we'll try to what, finish off the second module here. The remaining part, actually that PLL part, right, I'll be, as I told in previous session, I'll be addressing it in offline videos, right? We'll move on to the third module, right? So that for PLL, maybe I may need 1 hour 15 minutes to 1.5 hours, right? So that part, and I have already shared some solved out examples by Prasad sir in Canvas, right? So you are supposed to see that, not the video without any audio, right? So so in next class, that is tomorrow, we'll start with third module, right? So that's it for today. So if you have any doubt, please feel free to ask, right? So should I share this thing, whatever I am writing on this whiteboard, right? Should I save this and share? Will it be helpful? So I need to know your response, right? So whatever I have written on this whiteboard, should I be sharing this to you, right? Okay. Yeah, I can share that, right? Apart from that, any doubt you have, right? Can anyone tell me your opinion about this topic, right? Yeah, whom should I ask? Yeah, any volunteer. I'm not asking anyone. Anyone can boldly come forward and give me a Suggestion, no one. Okay, maybe what I can do is, right, as we have finished two modules and one internal test, right, I'll share a link for you to give feedback. It will be that you don't have to write your name, right? You don't have to write your yours, and even I won't be collecting your mail IDs. That you can give your feedback, right, on this particular subject. I request you to give constructive feedback. How we can improve the session. If I right, what is that I can do so that you will be able to appreciate the concepts in a better way. So if you have any complaints, also you can write that. Not a problem, right? So I'll share a feedback link in Canvas. I request everyone to what, fill in that and submit. Or else if you're ready to give some oral feedback, that would also be great. Right? If anyone want to give any feedback, no, you normally don't do that, right? So maybe I'll share a Google form. You can give your feedback there. Right. So in this session, so what we have seen is, maybe I should quickly wind up. So in direct method, we are using a frequency discriminator. A frequency discriminator consists of a slope circuit and an envelope detector. Right. A slope circuit, we have seen what should be the transfer function of slope circuit. Right. That is h1 of f. Right. Then, yeah. Someone was asking something. No. Yeah. Okay. So then what we did is we found s tilde of t. Then we converted this entire thing, the first part, that is slope circuit part, into its low pass equivalent. Then we found low pass equivalent of S1 of t. Then we converted it back into the band pass equivalent. Then we identified what was the envelope. Right. The envelope of low pass equivalent is equal to what, magnitude of the so envelope of S1 of t. We found it is equal to what, magnitude of this low pass equivalent. Right. Envelope of S1 of t was nothing but what, magnitude of low pass equivalent. That we found out. Right. So then we identified the envelope. It has a DC bias term. So if you have to eliminate that, we should have a balanced discriminator, frequency discriminator. For that, we added a slope circuit in parallel, right? And that particular slope circuit, which is intended to eliminate the bias term, it should have a frequency response given by h2 tilde of f is equal to minus, h1 of minus f, right? H1 of minus f. That is mirror image of that of h1 tilde of f or h1 of f. You can tell, right? So not h1 of f, a mirror image of the low pass equivalent, right? So then we have seen this balanced slope circuit can eliminate the DC bias term and give us a scaled version of our M of t or baseband signal, right? And we have even seen a practical implementation method of dual slope circuit, dual discriminator circuit. So we have actually what, a slope circuit given by an LC tank circuit. It's obvious an LC tank circuit's impedance or the gain provided by it to any input, it changes according to frequency, right? So whenever frequency changes, the output amplitude also will change. So this LC tank circuit act as a slope circuit, and we have a envelope detector followed by that. That envelope detector, like, clips off the negative part, right? And diode clips off the negative part, and this low pass filter or like smoothing filter, it actually what, like just like how we have smoothened out the ripples in if you, just like how we have smoothened out this rectified output using a filter, same thing, right? Same thing is happening here. So that half cycles, right? From that half cycles, we will get the envelope back, right? By passing through a filter. That's what is happening, right? So that's all about today's session. So next class we'll start with third module, right? I've taken some 10 minutes extra, so please forgive me, right? Yeah. So thank you so much. So now we can leave. If you don't have any doubt, you can leave, right?